India just changed its fighter jet industry forever. For decades, India's military aviation industry operated under a familiar model. Aircraft were designed by government organizations, manufactured primarily by state-owned companies, and supported by a network of suppliers. This approach produced important platforms such as the fighter and the 30 AMCA assembly program. However, a major shift is now. India has opened the door for private industry to participate in the manufacturing of its most ambitious combat aircraft project ever, the Advanced Medium Combat Aircraft, or AMCA. At first glance, AMCA appears to be just another fighter aircraft program. In reality, it represents something much larger. It is an attempt to transform India's aerospace industry from a government-dominated structure into a competitive industrial ecosystem capable of producing advanced combat aircraft at scale. To understand why this matters, we first need to understand what AMCA is. The Advanced Medium Combat Aircraft is India's planned fifth-generation stealth fighter. Unlike fourth-generation aircraft such as the or the 30 AMCA, AMCA is being designed for a battlefield where survival depends not only on speed and maneuverability, but also on information dominance, stealth, networking, and sensor integration. Modern air combat is changing rapidly. The fighter aircraft of the future is not simply a machine carrying missiles. It is a node in a larger combat network. It receives information from satellites, airborne early warning aircraft, ground stations, drones, and other fighters. It processes that information in real time and delivers a complete picture of the battlefield to the pilot. This is where AMCA enters the picture. The aircraft is expected to feature internal weapon bays that reduce radar visibility. Unlike external weapons mounted under the wings, internal bays preserve the aircraft's stealth characteristics. The design also incorporates advanced shaping techniques intended to reduce radar reflections from multiple angles. However, stealth is only one part of the equation. The real advantage of modern fifth-generation fighters comes from sensor fusion. Traditional aircraft often display information from separate sensors independently. Modern fighters combine radar data, infrared tracking systems, electronic warfare sensors, communication systems, and external sources into a unified tactical picture. The pilot spends less time interpreting data and more time making decisions. This capability is one of the reasons aircraft, such as the F-35, have changed military aviation. They function not only as fighters, but also as information hubs within a larger network. But while AMCA's technical specifications attract most of the attention, the most important development may actually be occurring outside the aircraft itself. The real story is manufacturing. For decades, Hindustan Aeronautics Limited occupied the central position in India's fighter aircraft manufacturing ecosystem. While private companies supplied components and subsystems, final assembly and large-scale production remained heavily concentrated within government-controlled organizations. The AMCA program introduces a different possibility. Major private sector companies including L&T, Bharat Forge, and others are expected to play increasingly significant roles in manufacturing and production. This may appear to be a simple procurement decision, but its implications are much larger. The United States did not become an aerospace superpower because of a single aircraft. It became an aerospace superpower because it built an industrial ecosystem. Multiple companies competed, innovated, specialized, and continuously developed expertise across generations of aircraft programs. The critical question facing India today is not whether it can build one advanced fighter aircraft. The critical question is whether it can build an industrial system capable of producing advanced aircraft continuously for decades. This distinction is important. Building a prototype demonstrates engineering capability. Building hundreds of aircraft demonstrates industrial capability. Many countries have developed impressive prototypes. Far fewer have mastered large-scale production, supply chain integration, maintenance infrastructure, software updates, and support. The challenge becomes even more difficult when we examine the technologies involved. Stealth aircraft are among the most complex engineering systems ever created. Every surface angle, panel alignment, inlet design, and structural component influences radar visibility. Small deviations during manufacturing can affect stealth performance. Radar-absorbing materials add another layer of complexity. These materials must survive extreme temperatures, weather conditions, vibration, and operational wear while maintaining their electromagnetic properties. Then there are sensors. Modern AESA radars contain thousands of transmit-receive modules operating simultaneously. Infrared search and track systems must detect distant targets while filtering background thermal noise. Electronic warfare systems must identify, classify, and counter hostile signals in real time. All of these systems generate enormous amounts of data. This brings us to networking. Modern fighters are increasingly becoming airborne data centers. Information flows between aircraft, satellites, drones, ground stations, naval assets, and command centers. The effectiveness of the fighter increasingly depends on the effectiveness of the network supporting it. However, despite all these challenges, there is one technology that remains the ultimate bottleneck: the engine. A fighter aircraft engine is often more difficult to develop than the aircraft itself. Modern jet engines operate under extraordinary conditions. Temperatures inside the turbine section can exceed the melting point of the materials used to construct the engine. Engineers overcome this challenge through advanced metallurgy, internal cooling channels, thermal barrier coatings, and single-crystal turbine blades. Single-crystal blades are among the most sophisticated components in aerospace engineering. Unlike conventional metal structures composed of multiple crystal boundaries, these blades are manufactured as a single continuous crystal structure. This significantly improves resistance to creep, fatigue, and high-temperature failure. The manufacturing process requires extreme precision. Small defects can reduce engine life or performance. This is one reason why only a small number of countries have successfully developed advanced fighter engines. Engine development represents a combination of materials science, thermodynamics, fluid mechanics, manufacturing technology, computational modeling, and decades of accumulated industrial experience. This is why many aerospace experts consider engine technology the final barrier separating aerospace powers from emerging aerospace nations. So where does India stand compared to other major powers? The United States developed the F-22 and later the F-35 after decades of investment in stealth technology, propulsion systems, avionics, and industrial infrastructure. China's J-20 emerged after sustained investment in aerospace manufacturing, electronics, and military modernization. Russia's 57 reflects a different approach emphasizing maneuverability, advanced sensors, and evolving stealth capabilities. India enters this competition later, but it also benefits from decades of global technological evolution and lessons learned from earlier programs. The challenge is substantial. The competition is intense. The timelines are long. Yet success should not be measured solely by the first flight of the aircraft. The true measure of success will be whether AMCA creates a self-sustaining aerospace ecosystem, capable of designing, manufacturing, upgrading, and exporting advanced combat aircraft across multiple generations. Because in the end, the future of India's fighter industry will not be determined only by the aircraft that emerges from the factory. It will be determined by the industrial foundation that makes the next aircraft possible.